This next chapter is all about thermochemistry, which has to do with energy changes. So we're going to talk about the energy changes involved in both chemical reactions and physical changes. So remember, phase changes are just physical changes, they're not actually chemical. But there is energy involved in both of those. And first we need to talk about how heat and temperature are actually different. A lot of people confuse those two words. So temperature, you actually have learned that definition in the past. So remember, it's a three-word definition. It's one of those ones you just need to memorize. Temperature is a measure of the average kinetic energy. And to say that in your own words, basically it means that the faster the particles move, the higher the temperature. And that is something that you can measure in the lab. So you could go over to a beaker, put a thermometer in, and you could get a measure of the kinetic energy of the particles. Heat is something that's a little bit different. So for heat, this is a transfer of that energy. So what I want you to do is circle or highlight the word transfer. That's the key word there for heat. And you can't actually measure the heat in the lab. You can calculate it. So if you put two things that are different temperatures near each other, there will be a transfer of energy. And by measuring the temperature where it started and the temperature where it ended, you can calculate the heat change involved. But it's not something that you can just go to a lab bench and measure the heat. You can measure temperature, but not heat. And heat always flows from hot to cold. So if you put an ice cube on your hand, it's tempting to say that coldness is going into your hand. But there's actually no such thing as coldness. That doesn't exist. There's heat and then there's a lack of heat. So what happens is your hand, since it's hotter, energy is flowing from your hand into the ice cube, and it feels cold to your hand because you're losing energy. So the way that your brain tells you that it's cold is that it loses energy. So as the heat goes from your hand to the ice cube, it's going to feel cold to you. The units for heat are called joules, but it's spelled differently from like a diamond jewel. It's named after a scientist. And then sometimes we'll use units like calories. Calories tell you a measure of energy as well, just like the calories in your food tell you how much energy is in that food. In foods, it's actually a kilocalorie, which is a capital C, but we'll talk about that next week when we do a lab. And the conversion is that 1 calorie is equal to 4.184 joules. This is not in your reference packet, but you don't need to memorize it. I'll put it on the test for you. So let's do a few conversions. Hopefully you're getting pretty good at conversions by now. Just going back and forth between calories and joules. Always start with what you're given in the top left corner. Bring the unit of calories down diagonal and put joules on top because that's what you're looking for. And then plug in your numbers. So 1 calorie is equal to 4.184 joules. Go ahead and pause this video and try the next 3 and then check your answers. And the next two words are actually really important, and luckily they're pretty easy to figure out. So exothermic, if you think about the prefix exo, it sounds like the word exit, which is to leave. So an exothermic reaction is a reaction that gives off energy. It's going to release energy from the reaction. And since it's releasing energy, when you touch the outside of a beaker that is exothermic, has something exothermic in it, it's going to feel hot to your fingertips. And if you write the equation, you see how A and B are over here, and then C and D are over here, but the energy is on the right side. So that means energy is being released. The opposite of giving off energy would be taking it in, which is called endothermic. And again, it's a pretty easy word to figure out because endo sounds like in, and thermic means heat or energy. So endothermic reactions are going to absorb energy. And a lot of students tend to miss this question because they think through it wrong. So make sure you're not one of the students who miss it. People start to think that if it's absorbing energy, it means it's getting hotter, so it would feel hot to your hand. And that's actually not what happens at all. If it's absorbing energy, it means that when you touch that beaker, it's going to take energy from your hand just like an ice cube would. And so your brain tells you that it's having energy taken from your hand by telling you that it's cold. So make sure that you don't think through that the wrong way. Endothermic reactions are going to absorb energy from your hand, which actually feels cold. So notice that energy is on the reactant side because you're starting with energy. And I want you to pause the video and take a few minutes to decide if you think each of these is exothermic or endothermic. And you can just write exo or endo in your notes. Once you've taken a minute to do that, you should check your answers. So the first one is exothermic. Number 2 is endo. Number 3 is endothermic, because this is your unit of energy right here, the 129 kilojoules. And it's going in because it's on the reactant side. For number 4, here's your energy, and it's on the right side, which means it's coming out. So that's exothermic. And baking bread is one that a lot of people tend to miss because they think of baking bread as being hot, but remember the heat is not coming from the bread, the heat is coming from the oven and going into the bread. So to bake the bread, it has to absorb heat, so that's going to be endothermic. 6 and 7 are both burning something, and anytime you burn something, it's releasing energy, so that's going to be exothermic. 8 you probably learned in biology is endothermic because you have energy from the sun. Number 9 is the opposite of photosynthesis, so that's exothermic. Notice that you're getting energy, where it says for energy. And then electrolysis of water is when you shoot electricity through water, so that would be endothermic. So just to review, exothermic is releasing energy, it feels hot, and it's going to be combustion reactions, anytime you burn something. This next part, a lot of people tend to miss too. So if it's exothermic, if you start with a certain amount of energy and you release some energy, that means you're going to end with a lower amount of energy. So the energy of the reactants is always going to be greater than the energy of the products if it's exothermic. So if we were graphing it, it would look like this, where the reactants are higher than the products because they gave off energy and they lost some of it, so now they have less as products. You would think, if you hadn't taken any chemistry, the graph would look, oh, first let's build an energy. So the energy of the reactants, like I said, is on the left, and the energy of the products is on the right. And you would think if you didn't know any chemistry, it would look like this, but it actually does not. The graph is not a straight line like that. It looks like this. So don't draw that straight line. You want to draw the hill. And the reason it has a hill like that is because all reactions, whether they're endothermic or exothermic, they have to gain a little bit of energy to get started, and we call that the activation energy. And the main thing people miss about that is they try to draw the arrow from the top of the hill all the way to the x-axis, and that's incorrect, because you're starting with a certain amount of energy. So you don't have to gain all of that energy, you just have to gain the difference between where you started and the top of the hill. And then the last thing on here that you need to know is the difference between where you started and where you ended. That's called the enthalpy. We're going to talk a whole lot more about that later. That is the heat of the reaction. Take a few minutes and copy this graph down. And then go ahead to the next one once you've finished. Just to review, for endothermic, it's an absorption of energy. And remember, this one's going to feel cold when you touch it. An example is shooting electricity through water to break it apart. And in terms of the graph, since you're gaining energy, the reactants are going to start at one energy level. And since they're gaining it, they're going to go up. So your products are going to be higher than your reactants, or have a greater amount of energy. So it's going to look more like this, where you start low and end high. And again, if you didn't know any chemistry, you would think that it just goes straight up, but it actually has the hill on it. So don't forget that all reactions are going to have that little hill. And that's because you have to gain a certain amount of energy to get the reaction started. But remember, the energy that you gain is not starting at the bottom, it's starting at the reactants. So since you already started with this much energy, if you just go to the top of the hill, that's how much energy you'd have to gain to make it turn into the products. And the word for that is activation energy. And then the last thing on here is the difference between where you started and where you ended. And again, that's called the enthalpy, which is the heat of the reaction. So if you put your pencil on the reactants and go straight up to the products, that's the enthalpy. So let's write a few of these vocabulary words down. We have activation energy. This is the amount of energy needed to get a reaction started. And remember, for this, you're going to start at the reactants and go to the top of the hill. This is required for both endothermic and exothermic reactions. No matter what kind of reaction it is, you always have to have some energy to get it started. And we need to do one more graph because we need to talk about catalysts. And you probably learned about these in biology. There's two things you need to know about catalysts. The first is that the whole purpose is that they're going to speed up the reaction. But for chemistry, you also have to know how they do that and the ways that they lower the activation energy. So basically, they take the hill of energy and they bring the hill down so it's a shorter hill. So if the reaction needs less energy to get started, it's going to go a whole lot faster. So for example, if this is our normal graph where we have reactants and products, notice that this is exothermic because the reactants are higher. They lost energy. Your activation energy, notice, is from the reactants to the top of the hill. If you add a catalyst, here's what it would look like. Notice that the hill came down, it's a little bit shorter, and so it reduces the activation energy. And so now the reaction can happen faster. And there's one more thing you might be asked about, and that is the name of the thing that's way up here at the top. So once it reaches the top of the hill, it's no longer a reactant anymore, but it's not quite a product yet. It's kind of an in-between state that's very high energy because it's at the highest peak there. And that's called the activated complex. And the energy of that would be the entire amount from the x-axis to the top of the hill. So activation energy, you start at the reactants and go up. The energy of the activated complex, which is the thing at the top, is the entire line right there. And the problem with that word, notice how similar these two words are, activated and activation energy. So it's easy to get these two confused. So make sure you separate those vocabulary words in your head. Activation energy is from the reactants to the top. Activated complex is the thing that's formed once it reaches the top. So this is the activated complex is what's at the top of the hill, and it's no longer a reactant, but it's not quite a product yet. And it is very high energy. And that is it for today. The first worksheet in your packet should have a picture of this graph, and you should be able to answer those questions. So I want you to look at worksheet 1 and see if you can fill in the answers to those questions.